Hi folks, I'm just going to do a little quick review on linear oblique asymptotes. Okay, so one place where we see linear oblique asymptotes is when we're looking at the end behavior of certain rational functions, and in particular when we're looking at a rational function whose degree in the numerator is 1 larger than the degree in the denominator. Okay, so for example here we have a cubic over a quadratic. Okay, so in general, we know that the numerator is going to grow quicker than the denominator. So that's why the end behavior will be going to either positive or negative infinity. Okay, but in this scenario here, we can actually say more. We can actually explain how it's approaching positive or negative infinity, and it does so by approaching an asymptote, which looks like an oblique line, meaning not a horizontal or vertical line, but something that's at an angle. Okay, so first things first, we could work with the equations that we have here, the expressions that we have here, and the way in which we determine the oblique asymptote is to actually divide these two expressions. Okay, but of course we know that when we're dealing with rational functions, what we should first try to do is see if we can simplify. Okay, and since these both look factorable, I'm going to factor and see if I can actually simplify this here. Okay, so in the numerator, cubic, hopefully you notice that it's a good candidate for grouping. Okay, so if I take out the x squared there, I'm left with x minus 1, and take out a negative 4, I'm left again with x minus 1, so this is going to work out nicely. And the denominator looks like it factors pretty nicely, so x minus 2 and x plus 1. Okay, so I keep going here. So I have x squared minus 4 times x minus 1. Okay, and lastly, this difference of squares, x plus 2, x minus 2. Okay, and I see that I will be able to indeed simplify this here. Okay, so we see that the x minus 2's reduce, so I'm just left with x plus 2 times x minus 1. Okay, and of course this is only true if x is not equal to 2. Okay, now when it comes to end behavior though, we don't care if, whether this function is defined at 2 or not. We're talking about end behavior. We're talking about very large or very small x's. So that means that instead of working with this expression, okay, this one here will have the same behavior when x gets very large or very small. Okay, because remember, these two are equivalent at every point other than x equals 2. Okay, so that means that when we do our division here, we can actually work with something where we're dividing a linear factor, in which case we can use synthetic division. Okay, so first thing we need to do though is expand this here. So we have x squared, so this will be plus x minus 2 over x plus 1. Okay, now how do we justify that we're going to have a linear oblique asymptote? So the first thing is to rewrite this in a different form, is to rewrite it as the quotient plus the remainder term. So we're going to have to divide this here, and I'll use synthetic division. So we've got 1, 1, negative 2. Okay, and we're dividing by x plus 1, so we've got our negative 1 on the outside here. Okay, so bring down the 1, multiply, negative 1, 1 plus negative 1 is 0. Okay, negative 1 times 0, well, obviously still 0, and so my remainder is just negative 2. Okay, so let's remember what this expression represents. This tells us that this quotient can be rewritten as my quotient x plus 0, so no constant term, plus, okay, my remainder divided by my original divisor, x plus 1. Okay, so my claim is that this linear function here represents the oblique asymptote. Okay, and the justification for that is that this term, remember, we're only interested in x getting really, really large, is this term approaches 0 as x approaches positive or negative infinity. Okay, so this function here, which can be written as x plus this extra term, well, this extra term starts to disappear as x gets very, very large. So that means that this function starts to look more and more like the function y equals x as x gets larger, small. So y equals x is called a linear oblique asymptote. Now, by the way, we would have gotten the exact same quotient had we divided this cubic by this quadratic, although of course we would have had to use long division instead of using synthetic division in this case here. Okay, so that's our recap. Or actually, let me do a recap here. So if you have a rational function whose numerator has a degree 1 larger than the denominator, you can use long division, and of course do that. Or in this case here, we were able to use synthetic division on the simplified version to determine the linear oblique asymptote, which is just given by the quotient of that division. Okay, that's it for this one.